All right. So what we'll do today is I'm going to finish up, values, numbers, and bases, because there's one little activity at the end of that document that I want to kind of bring you to your attention. So let me go there first, and then we'll move on and talk about how to add numbers in binary. So I'm going to bring this up and just scroll all the way to the end. And there's an exercise. So at the very end here, it says right here, this is an exercise to write a general purpose program to do base conversion. For flexibility, make the base a part of the input. The program should get the base of the input, the base of the output, the actual input number, and print the converted number. Okay? So it's really just an example. Okay? So what you do is you basically you have to have 3 numbers as the input, and there's only 1 output. The 3 things that are the input, 1 is going to be the base of the input number. The second one is going to be the base of the output number. And then the third one is going to be the number in the base that you specified earlier. And then the output is going to be the same value, but represented using the new base. Is that okay? Does everybody understand, what this kind of quote-unquote general purpose base conversion program is supposed to do? Okay? So from your C and C++ class, you actually have everything that you need to know to get this working. Okay, along with the content of this particular document. That gives you everything that you need to use in order to get this program to work. So, I would say, give yourself about a week to get this to work. So that means, next Tuesday, I'll present my solution. Okay, so if you want to do it, that's cool. I think doing it is good because it really helps to reinforce, what you understand about base conversion. Because conversion to base 2 is kind of what we mostly do, but sometimes we also convert to base 8 or base 16. Sometimes we have to look at base 16 numbers and figure out what value they are representing. So going through this motion, really kind of helps. Do we have any questions about the recommended activity, which is at the end of this particular document? So once again, this is not graded, which means if you want to do it in a group, hey, that's fine, not a problem. Okay? Yep.
When it comes to converting to base numbers that are higher than 10, should we just arbitrarily pick?
Yeah, I would just say stay with base 10 or lower. So don't worry about base 16 or base 12 or something like that. Mm-hmm.
And if we do it, do you want us to submit it?
No, there's no need to submit it. But I will give you my solution. So that way, you can download my solution, which is going to be written in plain C. I don't even do C++. And then you can compile my program, and then you can compare yours with mine. Okay. Yep.
What are the 3 inputs?
The 3 inputs are the base of the input number, the base of the output number, and then the actual number as the input. So the output would be the number representing the same value as the input number, but in the output base. So it can be something that's really oddball, like the input can be in base 7, and then the output is in base 3. All right? Any questions about this particular exercise? Okay, no questions? All right. If there are no questions about this one, we're going to move on and we'll start to talk about something that's a little bit more in-depth now, because binary addition is a little bit more in-depth, especially when we get to the part to optimize the circuitry so that we can perform addition as quickly as possible. So we're going to start with this one, and I know for sure that we are going to need the tablet today, so I'm going to start up the tablet. Okay. There we go. Let me get my... Oh, somebody left a hoodie/jacket in the lab, in the early lab, or possibly earlier. I cannot tell whether it was there already before the lab, But if you're missing a jacket, at the very back row, it might be yours.
I'm pretty sure it's mine.
It's okay, I locked the room, but there's another class coming in. I think it's still safe. Yep. Okay. All right, so let's go ahead and talk about addition. So when we talk about addition, let's do something that we already know how to do. Okay, base 10 addition. So we're going to deal with base 10 multi-digit addition. And we'll start with something that we should be able to do at this point. So we're going to say, what is 17 plus 26? Okay, there we go. And this is all in base 10, no tricks. This is just basically 17 plus 26, the two values, and they're all in base 10. So what do? You perform your addition column by column from right to left. That's because what is to the right is called the least significant digit, and what is to the left is the most significant digit. You cannot do the most significant digit or the more significant digit until you're done with the less significant digits. Does that make any sense? Okay. So the first thing we have to deal with now is to say, okay, what is 7 plus 6? It's 13, but we are not going to say it is 13. We'll say it is 3 with a carry of 1. Okay. So now we have a 3 with a carry of 1. So now we perform the addition of the second column, which is 1 plus 2. Okay. So the trick is we actually have two additions with the second column. The first one, the first addition, is adding the two digits that are given to you, which is this one here and this 2 here. 1 plus 2 is 3. But we are not done yet because we have a carry of 1 from the less significant digit. So now we say 3 plus 1 is 4. So we end up with an actual 4 as the most significant digit in this case. So are there any questions here about how this happens? No? Okay, well, I was hoping that there would not be any questions, so that's good. Because otherwise I would have to send that person to remedial math. Okay, that's cool. So when you learned addition in base 10, how long did it take you? If you don't remember, if you have younger siblings or nieces, nephews, about that age, that addition is not really that easy. Okay, the concept is easy, but to remember that 7 plus 6 is 3 with a carry of 1. To remember 8 plus 5 is 3 with a carry of 1. That's a pretty big table to memorize, and you cannot do anything until you have memorized that table. Is that making any sense? So now we're going to switch to binary numbers. Okay, so I'm going to use subscript 2 to indicate that those particular numbers are in base 2 to emphasize. So we have 0 plus 0 in base 2. So what do you think 0 plus 0 is in base 2? 0. Are you sure? This is base 2. It's not base 10. It's new to you. Are you really sure that nothing plus nothing is nothing? Yes. Okay, you're right. Okay, what about this one? 1 in base 2 plus 0 in base 2 is 1 in base 2. Are you sure? Yes. Okay. 0 in base 2 plus 1 in base 2 is 1 in base 2 because addition is commutative. Okay, cool. So the only one that we really don't know how to express is 1 plus 1, which is the same thing as asking in base 10, what is 5 plus 5? Okay, you will say 10. But how do you write 10 in this case? It is a 0 with a carry of 1. Okay, so I'm going to say this is actually 0, but I will use another column. Okay, so this is what I call the result of the addition. And then I'm going to use another column here to indicate the carry to whatever digit is to the left-hand side. So in this case, 0 plus 0 is 0 with a carry of, it has a carry, it's just that the carry is a 0. 0 plus 0. I'm going back to the
Oh,
first
the
one.
first one. Oh, okay.
Yeah, I'm going back to the first one. 0 plus 0 is a 0 with a carry of 0. Okay, that's cool. This is also a carry of 0. This is also a carry of 0. And this one has a carry of 1. Which is the same thing as saying 5 plus 5 in base 10 is 0, but with a carry of 1. What is the whole concept of a carry? I mean, getting back to the example here, 7 plus 6 is 3 with a carry of 1. Why do we have a carry?
Transferring a value to the next digit over.
But why is that necessary?
Because it goes over our base.
Because it goes over the base. Very good. Okay, so because it's in base 10, each place can only go from 0 to 9. If you try to represent a value that is more than 9, you cannot use a single digit. So you have to say, well, I can deal with this much. Okay, for the leftover part, which is the value of 10, has to go to the next digit. That is the whole idea of a carry in addition. Is that making any sense? Sorry? All right, cool. So now we look at binary addition, and this is the entire table. There's nothing else. Yep. Well, that's for the next digit to deal with. I don't have to deal with it. Okay. But this is it, okay? But if you think about in base 10, okay, so if I try to come up with the same table or the same lookup table in base 10, then I have a really big table because now I have to say, oh, 5 plus 7 is 2 with a carry of 1, and then we have 6 plus 7 is 3 with a carry of 1, and so on. That is a pretty long list. Even if you take into consideration that addition is commutative, it is still a pretty long list compared to binary. Because with binary, that's it, 4 entries. The first 3 entries are pretty much intuitive. The only entry that is kind of like, oh, we changed the rules a little bit, is the last entry. 1 plus 1 is 0 with a carry of 1. Is that making any sense? Is it okay so far? Okay, so to test whether it is actually okay at this point, whether you understand the concepts, we are gonna do some binary addition. Okay, we'll try out some examples. So we'll have 1, 0, 0, 1 plus 0, 0, 1, 1. And to emphasize that we are dealing with base 2, I'm gonna put a subscript 2 just to emphasize that this is not 1001, it is actually 1001 in base 2. Okay. I don't understand how the cricket is still here. You would have thought that it would have starved, right? There's nothing here for the cricket to eat.
It was your last semester too.
It's eating the wood.
Okay, so I'm going to do it this way, okay? Because remember, I said there were 2 additions. The first addition is dealing with the digits that are given to you. The second addition deals with the carry from the less significant digit. And that's why I'm separating it into 2 additions. Now this part is kind of important because even though in normal addition we do not write like there are actually 2 additions because we want it to be quicker, it is kind of important for us to do it this way when we're dealing with binary addition because ultimately we want to convert the logic to perform binary addition into circuits, into transistors, into gates, okay? And it is really important to spell everything out as much as we can. Okay, so can someone tell me what should go here? Which is, just the sum based on the digits that are given to you. 1 plus 1 is 0, very good. With a carry of 1. Where do I put that 1? I can see the gesture. Okay, from your perspective, that way. Yep. We'll put it here. Okay, so the bottom row, okay, this row here, are basically all the carriers. We start with a 0 because we don't have any less significant digits at this point, so we start with a 0. We assume it is 0, okay? Okay, cool. So now we perform the second addition. 0 plus, oh, okay, I have to change my hand here. So we have 0 plus 0 here being 0. Okay, we're done. Okay. Now we move on to the second column, or the second column from the right. Once again, we just perform the addition based on the digits that are given to us. So we have 0 plus 1 in this case. What is 0 plus 1? It's 1. Do we have a carry? Not yet. Okay, so if you don't have a carry yet, don't put a 0 in the next into the carry of the next digit. You just kind of leave it blank for now, because there are 2 chances that there might be a carry to that digit. Because now, even though 0 plus 1 is 1, this one is a carry from the less significant digit, which we have to add. So now we have 1 plus 1, which is 0 with a carry of 1. Okay, very good. So we have a 0 and a carry of 1 like this. Are we doing okay so far with this process? Okay. 0 plus 0, okay, 0 plus 0, because these are the digits that are given to us, is 0. So we don't have a carry just yet. And then we have 0 plus 1 being a 1, also without a carry. So if neither of the additions is generating a carry of 1, then you know for sure that there's no carry to the more significant digit. So this is the time when we can say, oh, since we do not have a carry of 1 from either of the additions, now we can just put a 0 here, because we have concluded that there's no carry of 1 from this particular column. Is that okay? Okay, so we're almost done here. 1 plus 0 is 1, and then 1 plus 0, this 1 plus this 0 is also a 1, and we are all done. There's no overall carry, so I'm going to just put it here. So there's an extra carry here that is a 0. The overall carry is 0. Yep.
I was wondering if there's a reason we're writing the carries like this instead of like normal addition. You might write it like at the top above the number or something.
That's a good question. So we'll answer that question when we are done with the R function and the C function. Okay. But is this okay? I mean, even though it looks a little bit different from how you would normally do like base 10 addition, the only difference is I really spell out the intermediate sum as well as the carry. And I really emphasize that there's another addition here between those 2 rows. Yes?
If there was a carry, would we make another row, or we're trying to keep it?
You mean, what if the overall carry is a 1?
Yeah.
Yeah, we just turn into a 1. Yeah, but we do care about that 1 extra carry. Okay, it's called carry out, which is of significance. So we, yep, go ahead.
The sum on the bottom is currently not, like, you have 2 1s and then you have the 1 after them in the middle. So, like, with that,
Okay, which row are we talking about?
the last row is
Okay, let me label the rows first. Okay, so I'll label the top one x, which is a number that is given to us. We'll label the second one y, which is also a number that is given to us. I'll label the third one q, which is the intermediate sum. I'll label this one as k, which are all the carries. I'll label this one as for the sum. Which row are we talking about?
the second and third digit in row K.
In row K, the second to
The second and third digit. Only
the second and digit. You mean these 2?
Yeah.
Okay, what about them?
Why do both of them exist?
Because 1 plus 1 is 0, but it has a carry of 1, so we put a carry here. And then with this one, it is because this 1 plus this 1 is 0, but with a carry of 1. That's why that 1 is there.
So that carry is for both operations?
Yes.
Okay.
Yep. Okay. Good question. Yep.
Can you leave that up for just a second?
Sure.
Is that? Yeah. Sorry.
And meanwhile, I'm trying to find the cricket.
There was one like crawling around here.
I think it's underneath here. Well, I'm gonna sense whether the air is going in or coming out. Looks like it's going in. Fumigator. But then it goes through the circulation and come out somewhere. Okay, so are we done?
Yeah.
Okay.
Thank you.
That's okay. Gave you some time to get acquainted with the quick. All right. So now we go back and look at the previous slide again. Now the previous slide is still significant in a way. It's funny, huh? Okay, so this one is still funny because let's not look at the result first. Okay, let's look at the carry. Look at this column, and look at the numbers here. So if I want to label these columns, okay, so let me label these guys. This is okay, like it's good. So this is X, this is Y, and if we just focus on X, Y, and C, okay, X and Y are given to us. C is what we're computing, right? I'm going to look at this as a truth table. In other words, I'm looking at X as a independent variable. It is independent to Y, which is also a variable. Don't you think this spells out every single way we can combine X and Y when each one is a bit? Yes? Okay. So when we look at the C or the carry column, does it resemble the result of applying a particular Boolean operator on X and Y? And that will be logical AND. That is kind of cool, because the concept of carry is arithmetic. It is calculation. It's based on values, right? But the conjunction operator is a logical operator, which can also be done using logic gates, which boils down to transistors. So that means, now we know how to perform. Now we know how to compute the carry using transistors. So that is kind of nice. What about R? If you look at the column R, it doesn't resemble anything that we are really familiar with, because we are used to conjunction. That doesn't look like conjunction. Conjunction is column C. It doesn't look entirely like disjunction or OR either, right? Because if it were an OR, then we would have a 1 here, but we have a 0 there. So it's not an OR either. It's definitely not, because not is a only takes one operand. Which one? What is it? Exclusive OR. Very good. Exclusive OR, but exclusive OR is not one of those things where we know how to translate using NAND. Okay, so is there another way to express exclusive OR, but only using AND or not? The operators that we know in C and C++. Okay, so let me kind of slide this one up a little bit, and we basically say X. Oops, switch back to the pen tool. So when we say X exclusive OR Y, when you see plus inside a circle, it means exclusive OR. So when we say X exclusive of Y, what else? What are some of the other ways to express this, but without using exclusive OR and only using the operators that we have already, that we are familiar with? Yep.
X not Y plus not X Y.
Yep, exactly. So we just want them to be different. So it becomes not X times Y, which means not X and Y, or X and not Y. Exclamation point means negation, and when we see the quote-unquote multiplication, it means conjunction. The plus, a regular plus, means disjunction in a logical expression. Those are the notations that we're going to use in this class. Is that okay? Okay, so I'm just going to re-emphasize what those things are. This is not. And the implicit multiplication is a conjunction, and then the plus is a disjunction. Okay. Now, is that okay? Just a notation issue. But the nice thing is, we know how to do negation, don't we? Using transistors. because negation boils down to NAND, and we know how to do NAND. What about conjunction? Well, we can also implement conjunction using NAND 2 gates. So that also boils down to transistors. What about the OR? We know how to do that too. We know how to boil down a OR into NAND gates, and every NAND gate can boil down to transistors. So that means if I go back to the top, that means we know how to implement R as a function using only transistors. We know how to implement C also only using transistors. Is that okay? Other than the cricket, it seems like no one is thinking this is profound. Well, thank you. But this is profound because once again, we are starting out with transistors. We get to the NAND gate. NAND gates will give us NOT or AND gates. And now we're using those to implement arithmetic operations. We're dealing with addition. Okay, so that's the significance. All right, so now I'm going to introduce some notation, which is also in the document that is linked from Canvas. So I'm going to use this notation, R as a function, to basically mean the result of the addition. Okay, so we already know, because we just talked about it, this is not x, y, or x not y. X exclusive or with y. Is that okay? So all I'm doing is, defining a function R to do what we already know how to do. But the importance is, this R will be used multiple times. Okay, what about C? Carry. The carry of adding x to y, and x being a single bit, y is a single bit, is, we know that already. It is just a conjunction. So it becomes really just xy. Is that okay? So the transition onto this slide is really just notation. I'm introducing R as a function. I'm introducing C as a function so that we have some notation to deal with, the exclusive OR, and some notation to deal with the conjunction. Are we doing okay so far with this? All right. So if this is the case, can we generalize and figure out, how to do a multi-bit addition, but only using these particular functions? So let's check out, this particular one. So I'm going to give you two numbers. One is x, but this time I'm not going to give you x as one whole thing. x0 is bit 0 of x. x1 is bit 1 of x. x2 is bit 2 of x. And I'm also giving you another number, which is y. Y has bit 0, y has bit 1, y has bit 2. Are we still doing okay so far with this? All right. And instead of assuming the least significant carry is a 0, I'm going to say, let's not assume anything. Okay. So K0 is now one of the input pins. It is given to you, it may be a 0, maybe a 1, but it is, we'll just call that K0. Is that okay? All right. So what goes here? Okay, let me use the mouse pointer here. So what goes here?
C.
No, not C. R. Okay, very good. So what goes here is R of what? X0, Y0. Okay, cool. And then what goes here? The sum. The sum, bit 0 of the sum is
Q.
Okay, we can call this Q. Okay, so this entire row is Q, which makes this guy, Q0. Okay, so you can use Q0 for this notation. So what's going to be bit 0 of the sum? What goes here?
R of K0 and R0.
Yep. So R of K0 and
R0.
not R0. We don't have an R0.
Oh, R of
Q0.
okay, Q0.
Close enough. Okay. So this is Q0, but instead of writing this whole thing, I'm just going to use Q0 here. because it's easier to write. Is that okay? And then we want to figure out then what goes here. That's a pattern, right? Okay, so this one is just r of x1, y1, and then what goes here? I'm just going to call it k1 here, and then we'll define what k1 is later. So I'm just going to put a k1 here, and then we'll define k1, let's say up here. So what do you think is k1? Well, it's definitely c of something, right? Because it's the carry. What is it? What is it the carry of? Okay, there are two c's. So let's focus on the first one. C of x0, y0. Okay, very good. So x0, y0. But we also have another c, don't we? And it's going to be what?
K0, Q0.
Yep. K0, Q0. Okay, so now how do we combine these two? Because we have two ways to generate a carry that would become K1. So now the question is, how do we combine these two? Well, we can combine these two using one of the operators that we already know. So now the question to you is it going to be AND or is it going to be OR? OR. OR makes a lot of sense because only up to one of these two can be a 1. They cannot both be 1s. They can both be 0s, but they cannot both be 1s. Yep.
Can you explain that part? How come they can't both be 1s?
How come they cannot both be 1s? Okay. All right. So let's think of okay. Let me think how we can prove this. Okay, because now it becomes a mathematical proof. So we are basically saying, okay, adding these two will give us a carry of 1. And we're also saying adding these two will also give us a carry of 1. So the question is, why is that not possible? Well, think about it. The only time these two can give you a carry of 1 is when x0, y0 are both 1s, right? 1 plus 1 has a carry of 1.
Oh, okay.
But when that happens, Q0 has to be a 0. And 0 plus whatever cannot generate a carry of 1. So that's why you can only have up to one of these additions giving you a carry of 1. They cannot both give you a carry of 1. Now, having both to give you a carry of 0 is easy to understand. 0 plus 0. Okay, if x0 is 0, if y0 is 0, then neither of these additions will give you a carry of 1. So that one is pretty easy to understand. But why you cannot have both additions giving you a carry of 1? That's the reason. Okay. All right. So we are almost done here. So then this one is still pretty easy to calculate because it's just the result of adding K1 and Q1. Is that okay? Do you want to deal with the third column because it's going to be pretty much the same stuff? Well, let's go ahead and deal with it. So with the third one, Q2 would be R of x2, y2. And then this is K2. But K2 is really just the C or the carry of adding x1, y1, or the carry of adding K1, Q1. Does that make sense to you? Okay. And then the sum of bit 2, or bit 2 of the sum, is really the same thing. Now we have a pattern, don't we? Because this is really just the result of adding Q2 to K2. Is that okay? And then the leftover carry, which is K3, okay, just to make this more complete, we now define K3, but you know the pattern already, because K3 is really just the carry of adding x2 and y2, or the carry of adding K2 and Q2. So there's no big surprise here. Is that okay? That looks really tedious to me. There's a lot of repetition. So as a developer, programmer, computer scientist, what is on your mind right now? Exactly. Okay, so that's the one thing that drives programmers. Okay, you look at something, it is so tedious, it is just repeating the same pattern over and over again. Then you extract the pattern. So when we extract the pattern, what is going to happen? Let's see. So we can define what is Q of I. Okay, so I is really just a bit position. So how can I define Q of I? How would you define Q of I? R of xi by I. Ooh, okay, that's easy. Okay, let's look at R. Let's look at sum. This is the sum row. So S of I is same kind of pattern, just change the letters a little bit, right? So what is that going to be? Ooh, I didn't touch it. R of Ki Qi. Okay, and Qi is already, we know how to deal with Qi, right? Cool. And what about Ki? There's a certain pattern to Ki as well. So if you look at Ki, which is kind of like generalizing these three things, what is Ki?
Q
It's the carry of xi minus 1, yi minus 1, or the carry of Yep. There we go.
Couldn't you write that as Ki equals Qi minus 1 Si minus 1?
Rewrite it as what again? Qi minus 1.
Minus 1 Si minus 1 plus minus. No.
The carry doesn't depend on the sum. The carry can depend on the digits that you're given with.
Oh, never mind.
Or the partial sum and the carry.
Never mind. Yeah, okay.
Okay. And if you translate all of this into logic gates, you now have an adder, right? And there are such things as exclusive OR gates in Logisim. So that means R can be done with a single gate. C can be done with a single gate. So now we have a full adder. Done. So why did I say that addition is difficult in base 2 and is complicated? Well, you can do it this way. But if you're an Intel engineer and this is how you implement an adder inside the latest and greatest Intel processor, you'll be fired. Why do you think you'll be fired?
Because the carry depends on the carry before it.
Exactly. So if you think about, okay, so we'll make this obvious, okay? You're dealing with a 64-bit processor. So at the very end, you care about K64. Okay, you plug in the equation, it's easy peasy, right? So K64 is C of X63, Y63, or the carry of K63, Q63. Okay, so let's take a look at this expansion here. How much time will it take me to compute X63 and Y63? It's a trick question, by the way. It's constant time, 0, because they are given to you. It's part of the input to the entire problem. So it doesn't take any time to compute X64, Y64. Excuse me, X63, Y63. Okay, so that means this part takes very little time to compute because all it is just a conjunction, an AND gate. Okay, let's look at the other one. Look at this one here. What about Q63? That looks a little bit more complicated. How much time does it take? Q63 is the R, or the exclusive OR, of X63, Y63. Well, it's not 0, but it's constant time, right? Because it is just whatever the input is, going through one single gate, and we're done. Not a problem. So the big problem that we have is K63. In order to compute K64, we need K63. And what do you think will look at the expansion of K63 will look like? It depends on K62, and then K62 depends on K61, and so on. So that means you cannot finish this calculation until the previous digit is all done. And that digit cannot be done unless the digit before that is done. Okay? So that means the amount of time to compute a number, an integer of a certain length, is linear to the length itself. To compute the sum of two 64-bit numbers will take twice the time of how long it takes to compute the sum of two 32-bit numbers. Is that okay? Then you go like, well, it is what it is, sorry. And then your boss says, well, sorry, you're fired. Why do you think your boss is going to say that? Because there's a faster way. And what is the name of that faster way? For those of you who read ahead of time. Carry look ahead. Okay, which is a misnomer, by the way, okay, because it's not really looking ahead, it's actually using all the bits available and doing parallel computations, whenever it's possible. Okay. So now I'm going to switch back to the notes because what is the derivation of the equation that I need to talk about now is a little bit tedious. I don't want to rewrite all of that stuff on the using the tablet here. So pretty much we are done with all of this stuff here. We define all of these terms already. Does that look familiar to you? Other than it is in square bracket and not in subscript. Q of I is the R of xi by I. K of I plus 1 is C of xi by I, or C of qi ki. Okay, basically the same thing. I just change the step forward instead of backwards. And then the sum is the R of qi ki. So same stuff. Okay, notation wise a little bit different, but otherwise it is the same. Okay, so we boiled everything down to logic gates and stuff like that. And exercise 5.1, if you want to do it, it's cool. If you don't want to do it, it's not too bad. Is to implement a 3-bit by 3-bit binary adder, but only using what we know at this point. By the way, this particular way of doing addition is called carry ripple, because the carry, when you look at how the carry bit is changing, it's rippling through the entire integer, 1 bit at a time, and that's why it's called carry rippling. Okay, which is slow, but it's easy to understand, relatively easy to implement. Okay, so I'm gonna skip this one, okay, and move on to, but wait, there's more. So we'll focus on this particular part of the document for now. So the bottom line is, how do I express k of I plus 1? So we'll do this row by row, just to make sure that we understand the derivation. And by the way, I'm not going to test you guys on the derivation because that's Boolean algebra. Okay, so in this class, our focus is not Boolean algebra, so I'm not going to test you guys on, how to derive this. But why do I talk about it if I am not going to test you on something?
So we can learn.
Exactly. Where else do you think when I explain the derivation of this thing here, the technique of doing this derivation, do you think it's going to be useful in some other classes?
Yeah.
Maybe in general, for programming or computer engineering or electrical engineering, that might be helpful. Okay, but I didn't do this because of those reasons. I did this part because I needed to convince myself of the validity of the derivation. Okay, so a lot of times, the documents that I post on Canvas, yes, it is, notes to you, but it's also notes to myself. Okay? All right, so we'll go through this one by one. So we'll go through the first row first. Does that look familiar to you?
Yes.
Based on what we just talked about. Okay. uppercase C versus lowercase c, but otherwise, pretty much the same thing. Going from the first row to the second row, is that okay? I got rid of the C and just say, oh, by the way, the carry of bit xi and the bit yi is really just the conjunction of xi, yi. Is that okay? We kind of talked about that, right? How we can convert the carry function, which is arithmetic, into logical operator, which is conjunction in this case. Is that okay?
I don't quite understand that one, to be honest.
Okay, let me. Okay, so it went back to all the way to here. The carry function can be done using conjunction.
Right, okay. I'm sorry.
That's okay. It's a good reminder that we are transitioning from arithmetic operations to Boolean operations, which is the magic of the whole thing. Okay, so are we okay with the second row?
Yeah.
Okay. What about from the second row to the third row? From here to here, I'm just expanding Qi. So Qi is expanded to the result of adding xi, yi, which is basically by definition. That's the definition of Qi.
Are your R's right here the same as to mean exclusive ORs?
Yes, this R does mean exclusive OR. Well, R itself is really the result of adding something, but it can be implemented using exclusive OR when you have base 2 addition. So in this case, yes, it can be done with exclusive OR. Okay? So are we still doing okay here? Row 3 is good? Sorry? You don't trust technology, do you? It's okay. I mean, I am not stopping you guys from taking notes. I'm just making fun. In fact, it's probably a good idea to check to make sure that my recording is still actually doing okay. Yep, it's still okay. So are we good?
Yeah.
With the third row? What about from the third row to the fourth row? So I'm expanding the R blah 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 to x and not y, or not x and y. Is that okay? That's just one way to express exclusive OR, but using logical operators that we know of. Okay, conjunction, disjunction, and negation. Are we still doing good? Up to the fourth row? What about from the fourth row to the fifth row? What does that look like to you? It's distribution. Okay, so in Boolean algebra, you can distribute addition over, you can distribute conjunction over disjunction, and you can also distribute disjunction over conjunction. Okay, so it's kind of a little bit different compared to normal algebra, but it does work. Okay. So this time, so that works. So are we okay with the fifth row at this point? So are we still okay, with this row? Okay. What about from this row to this row here? What is changed? I do the and true here, right? Can I just randomly add and true to whatever Boolean expression that I have without changing the value of the expression?
Yeah. I mean, it doesn't change anything.
It doesn't change anything. Right, so I can do this, right? It just uses up more black pixels on the screen. Yeah, because anything and true is whatever you start off with. I'm not buying that. How do we prove that? Truth table, very good. Okay, so every time we encounter something like this, it's good to kind of double check and make sure that it makes sense. Okay, so we have x, y, and y here. Okay, 0, 0, 0, 1, 1, 0, 1, 1. 0, 0, 0, 1. So where's my proof that anything and true is true? Which two rows? The second and the fourth, right? So when you look at this one, and this one here, it shows that false and true is false. True and true is true. So whatever and true is whatever you start off with. Here's the proof. Okay? All right, so getting back to the derivation. So that means this step is okay. I can introduce and true to whatever expression I want without changing the value. But that seems pretty stupid. Because in arithmetics, you can always say times 1, right? So why would I do that? The next step looks kind of dubious. Because instead of this just 1 here, I'm saying, oh, by the way, it is, or just, it seems arbitrary that I choose or ki. So now, are you guys buying this? No. Is true the same thing as true or blah, blah, blah? Whatever the blah, blah, blah turns out to be. How do we know?
Only one side has to be true.
Truth table, okay? So you're correct, but we can also prove this using a truth table. So let's go back to, but this time we have a disjunction truth table. So we got x, y as independent variables, and then we got x or y here. 0, 0, 0, 1, 0, whoops. 1, 0, 1, 1, okay? But this is disjunction or, so that means we have 0, 1, 1, 1 here. Where is the proof that 1 or whatever is 1? 1 or 0 is 1. 1 or 1 is 1. It is by definition of disjunction that we have that identity. 1 or whatever is just 1. Now it makes sense too. Intuitively it makes sense because with disjunction, if at least one side is true, the whole thing is true. So if you start off with true to begin with, there's nothing you can do to turn it into something that is not true if you're doing disjunction. Okay? But we can also prove it, really step by step using a truth table. All right. So I have just proven that it is okay to start with a true and turn it into true or something. Okay? In other words, it looks like I'm making things a lot more complicated than it needs to be because, you would think that I'm simplifying, right? Making things smaller. I'm actually making things bigger now. What about the next step? What did I do in the next step here? Distribution, very good. So x1, xi, yi, and 1, become this one here, and then xi, yi, ki becomes this term. So I'm just doing distribution here. Yep.
If you go back to the previous one where you were looking at the or, you looked at the 2 bottom rows. You looked when x is true and y is not true. Then when it's or, it'd be true, and then the last one where both are true. If it's or, it'd be true. But what about the first one when x would be false and y would be true? So that's if it's true, but if it's false and the other part, whatever it is, ends up to be true, that means it would.
Okay, so you're reasoning using substituting values into xi, yi, and so on.
Well, go back to the previous one where you were showing.
Previous what?
The truth tables, yeah.
Oh, okay, I see. Gotcha.
On the right hand side where you were showing for the x or y, you only highlighted the 2 bottom rows.
Yes.
What about the second row?
The second row is irrelevant to what I want to prove. Because what I want to prove is this is just that. True or whatever you want is really just true. That's what I want to prove. So that is why I only focus on the 2 rows that I have highlighted, because I start off with a true already.
When it's true.
The second one is a variable, so it can be false or true. But what I want to show is if you start off with true, doesn't matter what you OR it with, you always end up with true.
I feel like maybe a conjunction would work.
Conjunction works the opposite way. If you start with false, you can say false and whatever is always false. Is that okay? Okay, so it might take you a little bit more time to kind of absorb that one, but I'm just going to leave it like this, because the proof is there. It is just, it might take time to absorb it. Okay, what about from here to here? It's getting stupider and stupider, right? Because because from this row to this row, what did I do? I duplicate something, right? I made a copy of something and say, now there are two of these. This guy, right? There used to be just one of these. Now there's one and two of them. In other words, I'm trying to use the identity of x and x or x is just x. It doesn't change anything. Are you guys convinced that x or x is just x? I'm not convinced. So we go back here. Which two rows do we look at in the OR truth table to show us that x or x is really just x? Yep, you got it. 0 or 0 is just 0. 1 or 1 is just 1. So that concludes, we got the conclusion. X or x is just x. It doesn't change what we are dealing with. It just changes the representation. So at this point, you would think that I have lost my mind, right? Which can also be true, okay? But losing my mind is not why I'm doing this. It might contribute to something else, like the exam 1 and exam 2 questions. But not this. So what did I do from here to here? I think I'm just putting parentheses around stuff. So I'm using the rule of associativity. Okay. Okay. What about from here to here? The reverse of distribution, also aka factoring. Very good. Okay, so I'm factoring. Because this guy has got xi by ki, this guy has got xi ki. Group them together, and then whatever is left, which is yi, not yi, put it into a separate term. Okay? And same thing to the other side, except I'm factoring xi or not xi on the other side. Is that okay? What about from here to here? Looks like we're shrinking again. Why, how do I get this identity? How did I simplify to just true?
X or not X is always true.
Why is it always true?
Because if you say X is true, then it's true because that's the first part. If you say not X, then it's true because the second part is true.
Exactly, because in this particular disjunction, yi or not yi, one side is the opposite of the other one. If one is true, the other one is guaranteed to be false. If one is false, the other side is guaranteed to be true. But the point is, we know one and only one of them has to be true. But in the disjunction, if at least one side is true, the whole thing is true. And that's why we can guarantee that this expression here is always true, and this expression here is always true. That's using semantics. That's using the semantics of disjunction. But you can also prove the same thing using a truth table. Aren't you guys tired of truth table now? And this time we are looking at which two row? This one and this one. Because one is the negation of the other. You always end up with the one. Is that okay? See how truth tables are useful? With truth tables, you can forget about semantics. It's like, I don't want to explain this to you. Look at the truth table. Okay, so we are now convinced that this makes sense. And what about from here to here? How did I lose that one? Anything and true is whatever you start off with. X and true is just X. Once again, how do we know that? Once again, we use the truth table. Exactly. All right, which two rows are we looking at? Well, they're already circled. It's already circled because we have x, 0 and 1 is 0, 1 and 1 is 1. So the original value is preserved when you say blah, blah, blah and true. Is that okay? All right. So moving on. And from here to here is the reverse of distribution, factoring. Cool. But did I lose ki? It's still hanging around. So it doesn't seem like we have solved the problem of rippling, but we did change the form of the equation a little bit. Okay. In other words, we started off with something like this, and now we end up with something like this. Okay. All right. So if you continue to read, then I'm going to expand. So this part we can probably do it by hand. So we'll go ahead and, so I'm gonna write it down first. So give me a little bit of time, because I'm copying this. So we have ki plus 1 is xi yi plus xi plus yi, the whole thing, k0. Okay. Okay. Can you guys see this? Because I know the contrast is a little bit low. Is that okay? No? Darker color. Okay, fine. Ki plus 1 is xi yi, or xi or yi, the whole thing times ki. Here we go. So forget about this part. Okay. This is what we had, in the previous one. Is that okay? So let's say we're trying to figure out K2. Okay? Using this pattern, okay, it's pretty easy to figure out what it is. So it becomes K1, K1Y1, or Kx1, sorry, I said X, but I said K is X. Okay, I cannot read what I'm writing. X1 plus Y1, and then the whole thing times K0. Is that okay? Make sense? Yep. It will be K1. Oh, you're right. Okay. Let me fix that. It's K1 here. There we go. Thank you. But then it has K1. But we can expand K1 too. So now we say, what is K1? K1 is x0, y0, or x0 or y0, and then the whole thing times K0. Is that okay? But now we can use this trick. We can now say, hey, I can express K1 only using K0 and x and y. So I can do a substitution. Let's put it back here and see what happens. So now we can define K2 to be x1, y1, can't change that one, plus x1 plus y1, which is also copied from about here. But then we'll expand K1. In other words, K1 is now x0, y0, or x0 plus y0, K0 here. And then we'll do distribution. So this becomes x1, y1, plus x1 or y1, x0, y0, or x1 or y1, x0 or y0, k0. Is that okay? All I did is to do a substitution. Is that okay? What do you think is significant about this particular step? What is the significance of being able to express K2 using that big mess of a Boolean expression? Yeah.
It's only based on K0 and not proceeding.
Oh, that's right. It's not using K1, is it? Would it work with K3?
Yeah.
K4? Because if I can express K2 using only x, y, and K0, I can do the same thing to K3. Because K3 depends only on K2 and all the x and all the y's, right? But if I expand that K3, K2 to this, then it only depends on K0. So this is our ticket out of that whole rippling thing, because I don't need to depend on the previous carry anymore. Is that okay? So this is another profound moment of today's lecture. And the cricket agrees. The cricket has been agreeing the whole class. Yep.
Doing this as opposed to carry ripple, do we end up using more gates in total for every
Yes,
path?
we do. Yep, we do end up using more gates because now we have AND gate, OR gate, AND gate, OR gate, OR gate, and then AND here, and so on. So we do end up using more gates, but the actual overall time consumed is not going to depend on number of bits that we are adding anymore. Okay? Is that okay so far? So now we take this one more step, okay? So what we do is we say, let's define the p term here. So we'll define p of I, okay? I need to do a quick look here, because I have everything defined down here. Oh, okay, go back a little bit. Okay, so I'm reading this part here. We're defining p of I and g of I. So that p of I is the OR of the 2 bits that are given to us, and then g of I is the AND of the 2 bits that are given to us. So switching back to here. Is that okay? It's just by definition, okay? That doesn't take much time to compute, does it? It's just one single gate to go from the given bits x, y to the p term and a g term. Yep.
Is that what's supposed to be in?
Huh?
Did you write for us about it?
Oh, the one is AND. The G term is an AND. Sorry, you're right. Okay, this one is an AND. The other one is an OR. Okay.
Oh,
So if I keep using this terminology, then we can say Ki or K. Okay, Ki plus 1 is now G of I or Pi Ki. All I did was to turn xi, yi into gi because that's the definition of gi, and turn xi plus yi to pi because that's the definition of pi. Is that okay?
That's Ki plus 1?
Yeah, that's ki plus 1 on the left-hand side.
Sorry.
But we can do the same expansion, okay? It's just a convenience so that we don't have to say the conjunction of xy versus the disjunction of xi, x and y. Okay? So now the question is, do we have a closed form of what a particular k would look like? So let's check out the notes here. So in the notes, I have do some expansions. I have done some expansions. The first expansion is just K1, which is really easy, right? The second expansion is K2, which makes use of expanding K1. So when I look at K2, originally it relies on K1, but since I know what K1 looks like, I've expanded K1 here, and then we end up with this equation. Is that okay? Just overall speaking, okay? The actual derivation is a little bit tedious. But if I know K2, I can do the same trick to K3. So when I look at K3, this is the definition of K3. K3 by definition relies on K2. But since I know what K2 looks like, I expand that in place. So I look at K2 and go like, I know what K2 is. K2 is blah, 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 blah. So now I say, oh, whenever we look at K2, we just expand blah, 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 blah here. And then we now end up with a K3 that is only expressed using the P terms, G terms, and K0, which is an input pin. Is that okay? And you can probably imagine, hey, if I know what K3 is, I can do the same trick to K4. So the K4 will now be defined only using the P terms, the G terms, and also just K0. And that would extend to K5, K6, all the way. But each time I do the expansion, you can see it becomes incrementally more complex. Because K2 is like this, K3 is a bit more complex, has one additional term. Okay? So you can probably imagine K4 has one more term, K5 has one more term than that, and so on. But the question is, how long does it take to compute K2? How long does it take to compute K3? Can they be computed at the same time? So there are 3 questions here. How long does it take to compute K2? How many gate propagation are we dealing with here? One gate propagation is the application of one Boolean operator. It will take me one Boolean operator to compute G1, because that's a conjunction. It will take me one propagation to compute P1, and it will take me one propagation to do G0. But can these be done at the same time?
Yes.
They can all be done at the same time. So that means, in one single gate propagation delay, I can get G1, P1, G0, P1, and P1 is computed twice here, and P0, they can all be computed in one single gate propagation. Okay? Assuming your gates can take in as many inputs as you need, okay? The next level is really just doing this conjunction, and then the next level is doing the overall disjunction. Is that making any sense? We can now parallelize the computation. That's K2. What about K3? Do you think K3 would take more time, less time, or the same amount of time?
More time.
It's the same amount of time. Because even though it has more stuff here, G2, P2, G1, G0, P1, and P0, they are all computed in parallel at the same time. Yep.
So the farther we get out with our carries,
Yep.
that's the more gates that we need them.
It will need more gates, but it does not increase the amount of time
They're just all being done. at the
because
same
you
time.
have more stuff happening at the same time. Okay? But keeping our eyes on just K3, so in one gate propagation, I got all the P's and the G's computed, just like with K2. The second gate propagation is doing all the conjunctions, right? And then the third gate propagation, we do the overall disjunction, we're done. So it takes exactly the same amount of time to compute K3 as opposed to K2.
So in terms of that 3-bit pattern, does that
Yep.
mean that we have to set it up to go to K2?
No, you do not use K2. This is what you want to turn into gate logic. Now you can see that they share certain things, like G1 is used here. Okay, the P terms are always reused. So P1 is used here, is also used here, and also used here. So it's basically the same thing. You can use the output of P1 can go at in multiple places. Okay. What about K4 then? How do we know what about K64? Remember the Intel job that you don't want to lose? So how are you going to generate the expression for K64? Okay. First, you have to answer this question. Are you going to do this by hand? No. You hope not, right? Okay, so if you're not going to do this by hand, you need to understand the pattern, right? So that you can use loops to get it done. So instead of having you guys to do the generalization or the abstraction, I'm presenting it to you. So you look at this and go like, we have never seen anything like this, right? Well, you have. It is the same thing as the sigma versus the pi notation. So in other words, this notation here, okay, so I'm starting from the inside out. So this notation here is basically saying we're doing a big conjunction. What are we ANDing? What we're ANDing are a whole bunch of p terms. What p terms are we ANDing? Well, the first one is starting from I plus 1, and the last one is ending at n. And that's a huge conjunction, right? But that huge conjunction is being used in, you take this conjunction here and then you end it with GI. Okay? So that whole thing, from GI and then that whole big huge conjunction thing, this term is going to be inside a big disjunction. What disjunction are we talking about? This big B thing here, that's a big disjunction. So within that disjunction, I as an index goes from 0 to n. When I is 0, figure out what the highlighted portion is. Then you say or, I goes up by 1, becomes I equals 1. Then you figure out what happens when I equals 1, figure out what that blue thing is going to be. It's one big mess, okay? But that's how you do it. So when you're done with this side, this entire left-hand side of an overall disjunction, when you're done with this part here, then you look at the other side, which is a lot easier because we have a single K0 here, and then we have one big conjunction. So this big conjunction is actually not too bad because all it's going to do is go from 0 to n. So you're basically saying P0 and P1 and P2 and P3 all the way up to Pn. What n? N is determined by which k you're trying to figure out. So if you're trying to figure out what is k64, n is 63. Is that okay? So this can be done using loops, right? You will need 3 loops to do it. I said 3 loops because you need an outer loop, an inner loop. When this is all done, you have another single loop to perform the other side. But it can be done using control structure. Is that okay? So don't do this by hand, okay? If you happen to be hired by Intel and you have to do something like this, don't do it by hand. So I got this all figured out, for this is, by the way, this is called carry look ahead, okay? Which I think is a misnomer. It's not really looking ahead per se. It really is just saying, in order to figure out k of something, I just rely on the x, y, but I do not rely on the previous carry bit. That's the bottom line. So are we still doing okay so far? Okay. So I'm not gonna talk about the exercise just yet. Okay, we'll do it maybe next time. But when you read this document again, hopefully, focus on the big picture first. Okay, what is the major accomplishment of this entire derivation? Okay, we now have an adder that can deal with any number of bits, but only using logic gates. Is that okay? All right. So I'll meet with the late lab people over at 409, and then we'll talk about this a little bit more on Thursday. But if you're done with reading this, move on to the subtraction part. So if you're done with addition, move on to binary number subtraction, which is actually easier than addition. Alrighty, I'm gonna stop the recorder and I'll see you guys at the lab.